Welcome, everyone, to our Huntsman Knows How podcast. This is Donna Dare with Huntsman Communications, and we're excited to be discussing Huntsman's know-how in MIRALON carbon nanotechnologies and how Huntsman is enabling the technologies and trends of tomorrow. I'm joined today by our MIRALON experts, John Fraser, MIRALON Commercial Director, and Dr. Zach Lyles, MIRALON Program Manager. Hello, gentlemen, and welcome to the podcast.
Hi, Don. Thrilled to be here.
Hi, glad to be here.
If you've listened to the Huntsman investor calls over the past year or so, you've heard mention of this product known as MIRALON. So Zach, can you tell us more about it and why Huntsman is so excited about its potential?
Absolutely. MIRALON is a structural carbon product that is significantly smaller than most of our additives. It's going to be way smaller than what our eyes can see, and yet it's going to have one range that is in the millimeter length. These materials are going to be longer than your typical carbon nanotubes. And what that does is it gives us a fundamental advantage over our competitors. Our really long, really thin fibers are going to be able to create conductive networks that increase our conductivity in our materials. Additionally, it's going to be able to increase the strength of our structural composites.
And Zach, I think I read somewhere that it's something like 20 times the strength of steel.
Yes, it's actually going to be approximately 25 times the strength of steel at its weight.
And thinner than a human hair?
Significantly thinner than a human hair.
So really only visible under a microscope.
So it's even going to be specific microscopes. It's not going to be visible even under optical microscopes. It's going to require special instrumentation to view.
Super small, but super strong.
Yes, it is going to be considered one of the strongest materials known to man per weight.
Wow. So Zach, how do you make MIRALON? What's the process behind it?
So MIRALON is a unique process. It's going to take your methane, so your CH4, combine it with a few different co-catalyst materials, and what's going to come out the other end is our typical structural product that we've been talking about today, as well as clean hydrogen. So it's not only a product, but it is a process in and of itself. Nanoscale, to think of it largely, it would be a similar comparison in our day-to-day lives as a single soccer ball as compared to the Earth. That's about the size comparison that we're talking about.
So Zach, what do carbon nanomaterials look like when they come out of the reactor?
So they're gonna look like a black cotton candy. These long, thin fibers, as they grow, they form long enough pieces that they start to stick to each other, and it ultimately comes out as this very light, very strong material. It's going to come out in any different form, whether it's going to be a sheet, or it could potentially be a yarn, or in some of our more recent applications, we'll be collecting it as a pulp that increases the amount of applications that it can go into.
So, John, who would be interested in a material like this?
MIRALON has some fantastic properties, so any of your EV producers, so whether that's the OEMs or the tiers that produce their batteries, they would be looking at the electrical conductivity that MIRALON can bring to a battery for an EV vehicle. It could be our big cement players that are making concrete. MIRALON's flexural strength can improve the durability of concrete. In terms of tire applications, so your big tire producers, particularly for your EVs, where you get new challenges of higher torque, heavier weight, MIRALON can improve the performance of the tires. In thermoplastics, again used in automotive industry in huge tonnage, we can improve the mechanical strength and provide electrical conductivity. And then of course we have the traditional markets of space and aerospace, where MIRALON provides a level of light weighting and it's exceedingly great performance at very cold temperatures.
In fact, on NASA's Juno spacecraft, MIRALON was approved much faster than most materials due to the fact it was one of the only materials that hit the properties that NASA was looking for.
So one of the really neat things about MIRALON is it has all these properties that can find a niche in multiple markets. So it's got lightweighting, it's got conductivity, it has shielding effects, it has strength effects, it has flexibility and durability effects. It can even, when you apply a current, be used as a heater, which is quite a cool application.
So we talked about the versatility of MIRALON, the product, but there's also an environmental bonus to the manufacturing process itself, specifically focusing in on the utilization aspect of carbon capture, utilization, and storage. Can you tell me a little bit more about that?
Yeah, so MIRALON itself, the process in terms of the manufacture, it's taking natural gas or methane and it's separating that and it's giving you this fantastic MIRALON product, but it's also producing hydrogen. And as we move forward with the energy transition, there's a real desire and need for hydrogen. It's a fantastic product to have in addition to this wonderful MIRALON. When we look at the potential sources of fuel, we can use waste gas from flaring. Likely what we'll do is provide a solution for pipeline gas as it needs to move to a clean fuel. But there's also potential for us to use biogas as a source and provide a real green alternative where you take biogas, run it through the MIRALON process, produce hydrogen and the MIRALON that can go into all these different applications. Typically, when you're making hydrogen, you'd use an SMR process.
So John, let me just chime in on SMR. So that's the process of steam methane reforming, where you take your methane, you add it with water, and you get hydrogen out. Again, our process has fundamental advantages over traditional SMR. As you mentioned, we have a flexibility where we're able to take not only flare gas, but additionally pipeline gas, as well as other gas that would be disregarded by oil. So that allows us to have a much more robust process and have a lot more applications in contributing to the energy sector.
I think it's worth noting that in terms of the carbon footprint, an SMR typically would produce around 10 kilograms of CO2 for every kilogram of hydrogen. The MIRALON process is going to produce little to no carbon dioxide for every kilogram of hydrogen. So certainly a 90% reduction in the CO2 footprint is entirely possible using the MIRALON process. If we were to use a biogas as a feed to the MIRALON process, the process could actually be a carbon sink, where you'd be producing minus carbon dioxide for every kilogram of hydrogen that you produce, which is super exciting.
So, wait a second, this is below net zero?
That's entirely possible with a biogas source and the MIRALON process. You're absolutely right, Don. We can be below net zero.
Wow, so that's really exciting. So why aren't we seeing this everywhere already?
So I think, as you know, Don, Huntsman announced as part of its investor presentation that we were going to go forward with a pilot plant in 2023, and we're fully on with that at this moment in time. Zach's leading their efforts there, and maybe you can give us a word or two, Zach.
So Huntsman has put together an elite team that has allowed us to expedite our abilities of getting this reactor online. We have taken it from an idea to a reality. This reactor is planned to be online later this year with an additional larger reactor in the following year or two. In fact, this reactor will be one of the largest of its kind in America, and it will be located here in our backyard in Texas.
So yeah, we're moving forward at the moment with a 30-ton reactor. We've had the capability of producing small volumes up to, say, a ton a year in Merrimack for a good number of years now. But taking that step forward to take the pilot plant to 30 tons a year, and then we're looking to take it to 1,000 tons a year within the next year or two. It's a real big step forward. We know it's something our customers are looking for. They're looking to know that we've got the reassurance to be able to provide them with MIRALON in 1,000-ton quantities based on US production. These are two key differentiators that our customers are looking for, and that we're going to be able to provide, all based off the leverage that we're going to get from this 30-ton reactor. Around 250 tons of MIRALON would be required as a conductive additive for 1 gigawatt of battery power. Now, you'll have heard about the gigawatt factories going in. They typically talk about 10 gigawatts or 30 gigawatts. So if you were needing a 10 gigawatt factory, then you'd be looking at about 250 tons of MIRALON. If it's a 30 gigawatt factory, 750 tons of MIRALON. So you can see why customers are looking for that reassurance that they've got US supply of thousands of tons of this material. What the bigger reactor does allow us to do is also to work on our economics. When we're working at a ton a year, we have fairly unique economics, which allows us to sell the product into space and aerospace applications. When we move to the bigger reactor, coming online end of 25, beginning of 26, we have economics there that are suitable for EV batteries. They're suitable for tire applications, for thermoplastic applications, and for concrete applications.
So it's fascinating that Huntsman has seen this coming, has put the investment in, we're building the 30-ton, and we have a team ready to go to expand this even to the kiloton reactor in such a quick timeline.
Yeah, the scale-up is really an exciting timeline. What's more than that, though, within the wider energy transition, we're engaging with customers in the oil and gas industry that are asking us, how do we get to the 100,000-ton level? And that's going to provide our engineering teams a challenge that will take us out to 2030 and beyond.
It sounds like we're going to be putting a lot of reactors in.
I do hope so, yeah. This is such a great material. We want to make sure it's available in sufficient quantities to feed these markets.
What are the benefits of using the MIRALON process for the oil and gas industry?
In terms of oil and gas, we have a real opportunity. The oil and gas industry has got lots and lots of natural gas. When you burn natural gas, you release a lot of carbon dioxide. What the MIRALON process allows us to do is strip out that carbon in a solid form, producing clean burning hydrogen. We've worked with a number of really influential players. So we've worked with ARPA-E, the Advanced Research Project Agency for Energy. We've worked as well with the likes of the Carbon Hub at Rice University, where we've aimed to accelerate the energy transition and move to a more sustainable and reliable generation of green energy. So that's what we think we can offer to the oil and gas industry. We can help them as they make their energy transition.
The fact we can take any natural gas form and turn it into not only clean burning hydrogen, but as well as a high value carbon product.
Yeah, and I think that's super interesting because we know that the oil and gas industry have got huge amounts of natural gas. And if they don't do something different, then by 2050, when all these commitments about net zero have been made, then that natural gas is going to be stranded and worthless for the oil and gas players. So they're actively looking for an alternative, and I guess a better alternative than the current process of steam methane reforming. And the MIRALON process can offer that, can it, Zach?
Absolutely. Not only offer that, but produce these high-value carbon products that have so many different applications and can be consumed in such large quantities.
So are we saying that oil and gas producers could license this process, maybe put it on their property, or how would that work?
Yeah, so the oil and gas producers are currently providing end users with natural gas. When we talk about end users, let's think about the cement or the steel industry, where they're using natural gas to generate either heat or hydrogen for their process, sometimes both. And you could put a MIRALON process there, produce this structural carbon in a safe, secure manner, and then produce hydrogen locally to either a cement works or a steel works. And the hydrogen could either, in the case of steel, be used in the process. In the case of steel and cement, you could be burning the hydrogen to produce the heat you need to produce either the cement or the steel. So, really nice thought that you could drop in a MIRALON process at the end of the pipeline, produce hydrogen locally so you don't have to transport it, which is a challenge in itself and one of the factors that may challenge the adoption of hydrogen in a greater way. So we can produce that locally and just pipe it into that steel works or that cement works.
The fact that our process is adaptable, that it can be dropped in at so many different locations. It's a primary goal of our engineering team to make sure these reactors are flexible and able to go to so many different places and take so many different types of material and still produce clean hydrogen and still produce these high-value carbon products. So it's not just one application. It's not a purpose-built reactor. It's a reactor that takes our process and adapts it to many different things in many different ways. It allows it to be dropped in at concrete or steel and not only make, clean hydrogen, but it's also going to make a product that increases the strength of the steel and increases our flexural strength of the cement that it's going to be co-located with.
Well, the circularity there sounds like a great argument, Zach. One of the challenges that we have is if you can imagine a Venn diagram, which is basically two circles overlapping, the MIRALON process has some fantastic aspects to it in that in one of the circles it's producing hydrogen. In another sense, it's stripping the carbon out of the methane or the natural gas when you burn it. When it comes to getting support and funding, we seem to be just missing or slipping through the gaps because we do both hydrogen and pulling out the carbon, but because we're doing that, we're not entirely focused on hydrogen, and we're not there to capture CO2. We're there to prevent the formation of CO2. The really cool thing about the MIRALON process is it doesn't make carbon dioxide, or makes very little carbon dioxide. We capture the carbon in a solid format, which can either be stored or, as we've pointed out earlier, used in a myriad of applications, all of which can help further society and reduce the CO2 footprint in these end applications. We really become an enabler there for the wider oil and gas industry. We help them monetize the gas that they've got under the ground that's going to be coming out for the next 1 to 200 years, and it's not going to be suitable for them to continue to take that methane, burn it, and release all that CO2 into the atmosphere. We provide them a route where they can monetize without creating that environmental damage.
When we succeed at the kiloton scale, MIRALON will be a name that everyone knows.
Well, thank you, John and Zach, for your time and insights today. It's been a really fascinating discussion. It's great to hear about Huntsman's know-how when it comes to MIRALON carbon nanotechnologies and how it answers some of the toughest challenges around energy transition and the pursuit of carbon zero and beyond that. We invite anyone listening, if you have questions or want to know more about the material solutions discussed today, you can send those to huntsmanknowshow@huntsman.com. Thank you all for tuning in.